This time, I'm going to talk about how to choose the optimal learning rate with Python. Learning rate in neural networks is a hyperparameter that controls the step size at which the model's parameters are updated during training. During the training process, the model adjusts its weights and biases based on the error between the predicted output and the true output. The learning rate determines how much the model's parameters are adjusted in response to the error. When we train our model, we want to minimize the loss in our loss function. That means the target is here. We want our model reach here. So if the learning rate is too small, and then each time we just move a little bit, and it will take a lot of time. If the learning rate is too large, and then from this point we adjusted our model and it jumped to here, and then next time it will jump back here, and that means our learning rate is too large. With a reasonable learning rate, it should adjust our model like this, going towards the lower loss 1 time, 2 times, 3 times, and then eventually get here. And I will show you how it works with the model in Python code later. In my model, the training process is like this. I'm going to use the MNIST dataset for the training, and I will explain what this MNIST dataset looks like later. Step 2, the data is reshaped and normalized to a range between 0 and 1. Step 3, an autoencoder model is defined. Step 4, the encoder and decoder parts of the autoencoder are built. Use dense layers with specified activation functions. Step 5, the encoder and the decoder parts are connected to form the complete autoencoder model. Then, the autoencoder model is compiled using the Adam optimizer and binary cross-entropy loss. I'm going to explain this Adam optimizer and the binary cross-entropy loss function later. Step 7, the model is trained on the training data for a specified number of epochs and batch size. And finally, the training and validation results are plotted, and we visualize the training progress and the model's reconstruction performance. In this model, I used Adam optimization algorithm. Adam is an optimization algorithm that can be used instead of the classical stochastic gradient descent procedure to update network weights, iterative based in training data. It has several advantages. First, it's straightforward to implement, and it is computational efficient and less memory requirements. It's invariant to diagonal rescale of the gradients and well suited for problems that are large in terms of data and or parameters, and it is appropriate for non-stationary objectives. Further, it is appropriate for problems with very noisy or sparse gradients. Lastly, hyperparameters have intuitive interpretation and typically require little tuning. In this model, for neural network architecture, I used AE latent DIM16. AE latent DIM16 refers to an autoencoder neural network architecture where the dimensionality of the latent space is set to 16. I have another video talking about the visualization of latent space. If you haven't watched that video, you are welcome to watch that video as well. And for the loss function, I use a binary cross-entropy loss function. Binary cross-entropy loss is a commonly used loss function in machine learning, particularly for binary classification problems. It is used to calculate the difference between the predicted probabilities and the actual labels in a binary classification problem, and it penalizes the model more heavily for making incorrect predictions with high confidence. The binary cross-entropy loss function is calculated with this formula, and the capital N is the number of samples in the data set, and Y is the true label of the sample, because it is the label of the sample, so it will be either 0 or 1. And Y dash is the predicted probability of the sample belonging to class 1, because this is predicted probability, so it will be between 0 and 1. In the future, I will make another video talking about this binary cross-entropy loss function in detail. Now, let's take a look at our data set. MNIST is the acronym of Modified National Institute of Standards and Technology. So this MNIST database is a large database of handwritten digits that is commonly used for training various image processing systems. It is a data set of 60,000 small square 28 times 28 pixel grayscale images of handwritten single digits between 0 and 9. Look like this. Now, let's go to Python to check out all those images. Here, I loaded the database, and then I will pick up the first 20 images. You can see all those images are 28 times 28, and this is a handwritten 2, and this is 8, this is 6, this is 9, and we can pick up some same numbers to check the differences. Let's say we pick up number 7. If we run the program, you can see this is 7, and this is 7, this is 7. Although they all supposed to be 7, but it's quite different. So our goal is to train our model to recognize all those handwritten digits, although it looks like quite differently, and they all number 7. Now, let's go to our model. First, we are going to load our data set, and then we are going to change the dimensionality from 28 to 16, and we will define our activation function here. And as I mentioned before, for the autoencoder, we are going to use AE latent dim16. And here, for the optimizer, we are going to use addon, and for the loss function, we are going to use this binary cross-entropy function. Now, let's train our model. First time, let's use this 0.0005 as our learning rate. You can see this learning rate is very small, and if we run the program, now we got our results. You can see we train our model 70 epochs, and as we train our model, the value from the loss function decreased, and this blue line is the loss value from our training set, and this orange one is the loss value from our validation set. And now, if we change the learning rate to 0.001, we can retrain our model. Now you can see when we use learning rate as 0.001, we got this result, and the loss value is 0.13, and the loss value from validation is 0.1287. You can see this training process is quite time consuming. I will upload this source code and also the program for displaying this data set to my GitHub, so you can download it and change the parameters and try it by yourself. I summarize the training results with different learning rate and put it here. And if we have learning rate at 0.001, and we have the result like this, and this is value from the loss function, and this is for the training set, and this is for the validation set. If we have learning rate 0.01, it is 10 times larger than this one, you can see the value from the loss function for both training set and validation set became larger. That means it's getting worse. And if we have even larger learning rate, 0.02, you can see it is getting worse. And also for the validation set, the loss value of the loss function became jump around. And if we have very small learning rate, as I showed you with my Python code, the loss function will have value 0.16 about. And so this is not as good as our learning rate is 0.001. You can try to get your optimal learning rate, and if your learning rate is 0.0017, you can see the value of the loss function is 0.1274. This is very small, and you see the curve is very smooth. And how about if we have our learning rate a very large value? I put learning rate at 0.9. You can see the loss value from the loss function for both training set and the validation set start jumping around. You can see with very large learning rate, the results diverged. So this is something you want to avoid. And in this model, we just manually change the learning rate. So for each learning process, this learning rate is fixed. In the future, I'm going to make another video to show you how to decide this learning rate with the program without manually change its value of learning rate. This is how you can choose the optimal learning rate with Python. Please provide your comments and subscribe to my YouTube channel. Thank you.